is energy changes in chemical reactions. Reactions can be classified as either endothermic or exothermic. I think this is probably a review for you from earlier in your school career. An exothermic reaction transfers energy out to the surroundings. So it's releasing energy into the environment, and consequently the environment warms up. So the temperature of the environment goes up. So exothermic releases energy, feels warm. Endothermic reactions transfer thermal energy from the surroundings. So endothermic reactions absorb energy from their environment, and consequently their environment feels colder than before the reaction occurred. Okay, so hopefully these two definitions are definitions that you're familiar with, you've seen before. Okay, now we need to get a little more in depth about what's happening. So to quantify the heat flow associated with reactions, chemists use a property called enthalpy, which we abbreviate as H. I think the easiest way to think of this property is a vibrational instability. Because heat is actually a transfer of thermal energy, we calculate energy changes in chemical reactions based on change of enthalpy, delta H. And because this is a measure of energy, delta H is measured in joules. Joules is the unit of energy. Okay, so we don't measure enthalpy itself. We measure change of enthalpy in reactions. So when we measure change in enthalpy, what we're looking at here is the enthalpy of the products minus the enthalpy of the reactants. And that gives us our change in enthalpy, or our heat of reaction, the amount of energy associated with the reaction. How does that look? Hopefully that's it, right in the middle. Okay, now one thing to notice, you guys, is this thing is always within the system of the reaction. We're always comparing reactants to products. Always comparing reactants to products. None of this stands alone. Okay, it's a reaction system. We have to take the whole thing into account. Okay, so for an endothermic reaction, one that absorbs energy from its surroundings, the number one thing here is that products, number one, products have more potential energy reactants. Okay, so in an endothermic reaction, products So in an endothermic reaction, the products have more potential energy, more enthalpy, than the reactants. Okay, and in an exothermic reaction, it is just the opposite. The reactants have more potential energy. As well as enthalpy, more enthalpy. Than the products. Okay, so in an endothermic, our enthalpy, our products have more enthalpy than our reactants. So let's say this is 2 minus 1. Our answer here is going to be a positive. So for endothermic reactions, our delta H is always going to be a positive number. Exothermic, it's just the opposite. Okay, reactants have more enthalpy than the products. And so in this case, let's just say, simplify this, 1 minus 2 is negative 1. So in an exothermic reaction, the sign of delta H is always going to be negative. Okay, now for this next one, you guys will talk about this more and more. We're just getting this down so that you can stare at it. There's less energy in an endothermic reaction. There is less energy released forming product bonds than used breaking reactant bonds. And for exothermic reaction, it's just the opposite. There's more energy. Released. Forming product bonds. Than used Now, last but not least, one more point I want to make about these, keeping in mind, people, that we're going to talk about this so much more. Number 4. In an endothermic reaction, we make weak, less stable product bonds. And in an exothermic reaction, we make strong, more stable product bonds. So the more enthalpy in the molecule, the weak and less stable those bonds are, and the more potential energy they have. The more stable, the stronger the bond, the less potential energy they have, the less enthalpy they have. This is incredibly counterintuitive. Okay, but we'll talk about it. We'll talk about it in class. Okay, so weak bonds actually store more energy, believe it or not. All right, so let's do some problems. All right, so this would be an example of a problem we would see. Calculate the heat evolved when 266 grams of white phosphorus, P4, burns in air. So here is our balanced equation, and there is the heat, the energy associated with that reaction. The delta H of that reaction is negative 3,013 kilojoules. So, for every 1 mole of phosphorus, we utilize 5 moles of oxygen to produce 1 mole of tetraphosphorus dicoxide. And the heat associated, the energy associated with that reaction is negative 3,013 kilojoules. So looking at that delta H, is this an endothermic or is it an exothermic reaction? This thing is an exothermic reaction. How do I know that? Because the sign of delta H is negative. And what that tells me then, if I go back and look at my list, is that because it's exothermic, the reactants have more enthalpy than the products in that particular reaction. There's more energy released when the product bonds are formed than got used in breaking the reactant bonds. And those product bonds are strong and more stable. So if we, again, look at this reaction, energy is always used in breaking reactant bonds. Always energy is consumed. Figuring out whether the thing overall is going to be exothermic or endothermic depends on what kind of products we're forming. And it's when the products form more energy necessary going in, stabilizing that thing, or we've got excess and we can let them go. We can let some energy go. We don't know the final tally until these bonds are formed. Okay, so there's a lot of conceptual stuff here besides just the math. All right, so let's do the math for this thing. We want to know how much heat, how much energy is associated with burning 266 grams of this stuff. So our balanced equation gives us the number of pieces here, not anything about grams. So the first thing we need to do is we need to convert grams of phosphorus to moles of phosphorus before we can do anything. So we have 266 grams of P4. And the molar mass is 123.88 grams of P4 per mole of P4. And what this information tells us is that we have negative 3,013 kilojoules of energy associated with every 1 mole of P4 that is consumed. And so if we do this calculation, what we get is negative 6,470 kilojoules. So this is the amount of energy that is associated with burning 266 grams of phosphorus, and because it's negative, we know that that energy is being transferred out. It is an exothermic reaction. Okay, so 6,470 kJ evolved, or put out. Okay, let's do another problem. Let's say instead we want to know how much heat is involved with consuming 17 grams of oxygen. So let's start with something different. Let's say we've got 17.0 grams of O2. And we want to know what is the heat associated with that. What is the energy associated with consuming that many grams of O2? So again, this whole thing is given in terms of moles. So we're going to convert grams to moles, 32.00 grams of O2 per mole of O2. And then what this tells us is we have negative 3,013 kJ associated with consuming how many moles of O2? 5 moles of O2. So the mathematics here, you guys, is really pretty straightforward. Nothing difficult about it. Negative 320 kJ. Okay, so the math, again, is easy. Where did this number come from? How do we measure the heat? This is if the energy is given to us. But how do we do this? How do we figure out delta H for this kind of reaction? Well, that's what we'll do next. Okay, so again, you guys, this math, yeah, easy. This stuff, though, this conceptual stuff is just as important. And this is going to take, really, the whole year seeing it in different contexts before we can really master this. But this is something that you need to see, and you need to try to begin to make sense of this. And we'll talk more about this in class, of course. All right, that's all.